Hi everyone. Radioactivity is fundamentally a quantum mechanical phenomenon. If this picture here represents a typical nucleus, what's going on here is this is the distance from the center of the nucleus. If I'm a proton sitting out here and I get close to the nucleus, I feel the electrostatic repulsion. The potential pushes me away from the nucleus. Okay? So, on this energy diagram, the amount of energy required to get closer and closer increases until all of a sudden we get to a point where the strong nuclear force starts to come into play. And that strong nuclear force is very strong and basically overwhelms that electrostatic repulsion. So if I have enough energy for the proton to sneak over this barrier, it will fall into the nucleus, be attracted and trapped. And that's how the atomic nucleus is built. But remember, each one of these protons and neutrons are little wiggly quantum mechanical waves, as the picture shows. And this is essentially a potential barrier. And the crazy thing about quantum mechanics is that these quantum mechanical particles, though classically trapped, have a small probability of existing on the outside, tunneling through that barrier. And that's precisely why radioactivity occurs. Because even though the protons and neutrons are trapped inside the nucleus, every once in a while, a stray proton or a stray neutron finds its way outside through this quantum mechanical phenomenon. And once it gets out here, it's got a lot of energy and just flies away. Very energetic particle at that point. And so that's what we call radioactivity. Now, when radioactivity occurs, that's going to change the characteristic of the nucleus. And we call this transmutation, when the chemical property of the nucleus changes. Now, there are three types of radioactivity that were initially discovered. They call them alpha, beta, gamma because they didn't know what they were initially. The first is alpha radiation. Alpha radiation typically occurs when a proton sneaks outside of the nucleus. Now, when the proton gets outside the nucleus, it actually is very attractive to surrounding neutrons, and it actually pulls, usually, doesn't have to always, but usually pulls actually two neutrons and another proton, because the helium nucleus is a very stable configuration for these particles. And so when a proton sneaks out, it usually actually draws out a fourfold partnership, and that's what we call the alpha particle. It's essentially this helium nucleus that flies out with a lot of energy. Beta radiation occurs when a neutron sneaks outside. The neutron gets outside and it flies away, yes, but it also blows apart into a proton and electron, and usually that proton gets reabsorbed in the nucleus because it's still participating in the strong nuclear force, but the electron doesn't feel that nuclear force at all. It's the one that escapes. And so beta radiation is typically electrons flying out. And so when alpha radiation occurs, you lose protons, and therefore you move down the periodic chart. When beta radiation occurs, you actually gain a proton, and you move up the periodic chart. So these different types of radioactivity actually transmute and change the chemical nature of these particles. The third type of radiation, gamma radiation, is really nothing more than just classic electromagnetic radiation. It's the same thing that happens in an atom when an excited electron decays to its ground state. That's going to release a photon of light. The same thing occurs in radioactivity. Typically these protons and neutrons, when they escape, they leave the nucleus kind of in a highly energetic state. Well, that energy eventually gets released as electromagnetic radiation as that, that jiggling nucleus kind of drops down to a kind of a more stable state at rest. That is accompanied by a highly energetic form of electromagnetic radiation, which is called gamma radiation. Now, because this phenomenon is quantum mechanical in nature, it's all probability based. It may or may not happen, and it all has to do with this represents the probability of this happening. So what this means is that if I have a collection of these atoms, at any one time any one of these could fire off, but I don't know which one, and the rate at which they fire off I have no control over. It just has to do with the characteristics of the nucleus, right? And so what happens in a typical sample is, say you've got 16 atoms. After a certain period of time, let's say half of them decay. You're left with 8. After another period of time, these particles here still have the same probability of decaying as they did up here. The rate at which they decay is constant over time because this has nothing to do with time. It just has to do with the properties of the nucleus. And so if this has got a 50-50 shot at decaying, then in the next time period I've got another 50-50 shot, another 50-50 shot. So what you have here is a reduction in the total number of unstable particles, 16, 8, 4, 2, 1. Right? Eventually this will decay. The point is, for this period of time, half of the particles disappear. For the next period of time, half. This time period is called the half-life of the material and is completely controlled by the nature of the material. No outside circumstances can change the situation. So, for example, carbon-14. Carbon-12 is the more stable partner, but carbon-14's got too many neutrons. It's got 8 neutrons, 6 protons. And so it's radioactive. It has a half-life of 5,730 years. So every 5,730 years, half of those carbon atoms decay via radiation. And so this actually is how radiocarbon dating works, is that you take a look at your carbon sample, compare it to the amount of carbon it ought to have if it were alive today, and you can see how much, you can compare how much carbon-14 is left. The amount of carbon-14 gives you an indicator of how much time has passed since that sample was absorbing the natural ratios of carbon-14 to carbon-12. And that's how we estimate how old certain samples are.